on the bipolar transistors. Last time we have talked about the basic operation, and the conclusion was this plot. Okay. You can see this is the current from emitter to collector, and then this is the voltage applied to the base and emitter, and you can see exponential increase. And typically we can get the 60 millivolts per decade current. Okay, the slope is going to be somewhere around there. And the final equation is this. This equation has been plotted, the current against the voltage. Okay. So this equation predicts an exponential relationship between current and the voltage. Okay. And the slope is such and such. Relationship holds extremely well for IC transistors over many decades of current in general. And then the QB is the Gummel number, which is the dopant concentration in the base, is obtained by integration over the base region. Right? And you can see QB is typically well controlled to 10 to the 12, which is a very lightly doped concentration. All right, today we're going to discuss about the current gain. The main function of the transistor are two things. One is switching, and the other is amplifying. And we call that the gain instead of amplifying. Amplifying is not a proper word, as a matter of fact, because we are not going to produce anything new. It just to control the output with a small input, something like that. So we call that gain. All right. Now, the switching is almost the same to bipolar and MOS transistors, but the gain is very much different between these two transistors. MOS is more or less, it is used for, mainly used for the switching purpose, and bipolar, it can be used as amplifying functions. Now, if you look into, so it is very important to look into the current gain in the bipolar transistors. And MOS transistors, of course, it is very important to see the switching speed and things like that, okay, switching properties. So we have to emphasize on the current gain of bipolar transistors. And it has three terms which controls the current gain in the bipolar transistors. And then the first one is recombination in the neutral base region. Neutral base region means in the base except the depletion regions, right? That is a neutral base region, and that is a 2.3.1, and the other is hole injection into the emitter, and the number 3 is emitter base space charge region recombination. So these three factors determines the current gain of bipolar transistor as a whole. So let's look into these three factors more carefully. Well, let me see if you have bipolar transistors. Okay, this is emitter, base, collector. And then it says we have, as far as the current gain is concerned, we have three factors. 1, 2, 3 is important. And the number one is recombination in the neutral base. Recombination and neutral base. Okay, and then number two is hole injection into the emitter. Hole injection into emitter. And then number three is going to be recombination in the depletion region. Emitter base space charge recombination. Okay, so if you draw this thing into drawings, the first one is shown here. Here, the recombination in the neutral base means if the electron is injected in the base, we have a depletion region in emitter base junction and the depletion region in base collector junction. So except this depleted region, this is called the neutral base region. Okay, in this neutral base region, if electron is electron is injected into this base region, it should survive to be collected in the collector to get a gain. But somehow, if the injected electron has a recombination in the neutral base region before it reaches the collector, then that electron is not going to contribute anything to the current gain of the bipolar transistors. So that's what we mean by the recombination in the neutral base. So let's say we have a depletion region, so something like this, and electron is going to be injected and then get the recombination in the neutral region. Okay? And number two is a hole injection into the emitter. Means if you have a bias between emitter and base to inject the electron from the emitter to the base, it just means that you're going to have a hole injection from the base to the emitter at the same time. Okay? So this whole injection into the emitter is not going to contribute anything of a total gain of this bipolar transistors. So number two is also important. And number three is the emitter-based space charge recombination. Means we have a space charge region here in the emitter and the base, and then this electron is injected into the space charge region. This emitter-based space charge recombination is not related with the emitter injected into the base. It's just generation and recombination. Okay, the new electrons which has been generated in this space charge region is going to make a recombination in itself, and that is going to affect the total gain. And we are going to look into the details in the equations in this section. So let's start with the first section here, which is recombination in the neutral base regions. Okay. Recombination in the neutral base region. Okay. If we assume base is uniformly doped so that there is no electric field coming from the slope of the dopants, then the electron current and continuity equation says the current is going to be by diffusion flux only. Okay, so no drift current because no electric field in there because of uniform doping. Okay, and then this continuity equation is going to be, this is the transport equation and this is the continuity equations corresponding to that. And then we saw in the base, in the case of p-n junctions, generally we can have these equations. We have discussion in the diode properties, is exactly the diode properties. NP is the concentration of electrons in the p-type regions in the base, okay, far away from the interface. And NP naught is the equilibrium concentration. That is the interface concentration, and that is the equilibrium concentration. And we apply the boundary conditions. We know the concentration of minority carriers at x equal to 0 and x equal to xb. Okay, that x equal to 0 is here. This is x equal to 0, and then this here is x equal to xb. Okay, that is the base width. And with the boundary conditions, blah, 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 and then the current, the emitter and the collector, the ratio between these two currents is defined as a base transport factor. Okay? And there's alpha T. And in modern IC bipolar transistors, the XB is the length of the base, the width of the base, if you like. That is pretty much shorter than the diffusion length of injected electrons. Okay, we typically make this 10,000 angstrom to 3,000 angstrom. The XB. Okay, the diffusion length is to 1 to 10 microns. So we know the XB is much less than the Ln, diffusion length of electrons. So there's very little chance, as a matter of fact, for the injector electrons to be recombined in the base region. And there is a little recombination in the neutral base because of this, the physical parameters. Okay? And if XB, the base width is much less than the diffusion length of minority carriers, we can set that it's a linear, and then the transport factor becomes simplified to these values. And you can see the XB is the base width, and Ln is the minority carrier lifetime. And then since Ln is very much bigger than the XB, the alpha T is almost 1. It's very close to 1. It's typically 0.9994, something like that. Very close to 1. This implies the current gain is more than 1600, which is higher than the normally observed in IC polar transistors with 1 micron base width. Transport number is not usually a limiting factor in the current gain. It's enough, big enough. It means transport number is almost 1. We are not going to lose any injected electrons in the base. That's what it meant. Okay, the base current is going to be something like that. And then here we have a lifetime of the minority carriers in the base. Well, the next section is a whole injection into the emitter. We are going to have a electron injection into the base with the same voltage, and at the same time we're going to have a whole injection into the emitter from the base. So we have to take that thing into account. The dominant mechanism in limiting beta, the gain, in modern bipolar transistors is a whole injection into emitter from the base. And this process must occur because we do apply a voltage between base and emitter. So this is the configuration of the minority carrier concentrations in the emitter and base. And this is a long base emitter, and this is a short base, short emitter. Okay. Here, if we have a long XE, we have both cases, we make the base as small as possible. So we always have a narrow channel diode there in the base. We have a straight line of the minority carriers in the base. But we can have choice. We have a long base diode inner emitter, and then a short base in the emitter. So we can think of both cases. It's not that complicated. We just have a simple equations which is very close to this, to each other. It's just a linear thing. Now, the injection efficiency of the emitter is defined by the electron current injected into the base and the total current coming from the electrons and holes. Okay, that is the efficiencies we call injection efficiencies. It's pretty much reasonable, isn't it? And then from here we can directly see the gamma injection efficiency, the total current, the ratio of electron current injected into the base to the total current is going to be the injection efficiencies, and the injection efficiencies can be written with that equation. And the long diode approximation replaces XB and XE. That's a simple thing. Now, this equation is only correct in IC because base doping and emitter doping are not constant. Maybe it has a concentration gradient, but that is not severe assumptions. The modern IC structures, the concentration gradient is not that considerable. Well, so if you want to have a gamma, the efficiency, injection efficiency great, big, we have to make the emitter dopant concentration should be very much larger than the base concentrations. And this is typically done. We want to have a gamma number as small as possible for large beta anyway. So this is a typical case that we do in the fabrication. Making the emitter length is large, or alternatively by preventing whole recombination at the emitter constant. So when you make a whole, make the emitter length big, then hole injected into the base is not going to be collected at the junctions at the end, the emitter and the metal electrode. Okay, at these junctions, we always have the whole concentration is equal to 0, because that is going to be taken out to the outer circuit. So if you make it this long, then you have a less chance for the holes to be injected into the emitter. So we want to make the emitter as large as possible to have the gamma, the efficiency, close to unity. Okay? And base, of course, should you make very short. This is also desirable from the point of view of increasing the transport number, R per T. So that is related to the whole injection into the emitter. And the last section is emitter-based space charge region recombination. And see, this is a recombination happens in the space charge regions. The first thing is a recombination of electrons in the base, and here we are going to talk about the recombination in the space charge region. And let's see how we can develop the equations for this. Note that both alpha T and gamma efficiency and transport number are important of base emitter voltage applying to that the ratio of a collector to the base current is a constant independent of base emitter voltage. In practice, the ratio of two currents is not independent of collector current. At low levels, the dominant reason is recombination in the emitter base depletion region. So the important thing is at low levels of the emitter base voltage, now the recombination in the space charge region between emitter and base is going to tap. Okay? We saw in our p-n junction discussion that some recombination of the carriers moving through the depletion region will occur, and then that is the recombination current is going to be something like this. And then you can see, let me make it a little bit big so that you can see. Here, the important thing is we have a factor 2 here in the exponential term. You can see that the factor 2 is the characteristic of this recombination current in the space charge regions. That equation has been discussed in the p-n junction, which has not been discussed in this class, but it's very common in the p-n diode discussions. Okay? And with that equation, this current flows in the emitter-based circuit and does not directly affect the collector current. Thus, as I recombination current becomes important, the ratio of base current and collector current will change, and the dependence to here is important at the low level voltages. So that is the equation corresponding to that. And now summarizing our discussion, the current gain as a total is going to be a summation of these two. Transport number, efficiencies and transport number and the recombination, all those things has to be put together. I think I should. Yeah. That is related to the efficiencies, and that equation is related to the transport number, and this one is related to recombinations. And all those corresponding terms can be expressed in these equations, and the total equation is going to be like that. And if you plot the collector current and the base current with respect to the emitter base voltage, now you are going to have a slope corresponding to this and the term here too. And then this one, when you have small voltages, okay, then this term, the dotted line becomes important. You can see. So at high voltages, between the emitter and base, the space charge region recombination, which has been discussed in the section 3, is not important, but as you get low level injections, low level voltages between emitter and base, because of this 2, if you get this small, then it's going to be important, determining the current. So we can see that the collector current is proportional to the emitter base voltage in this fashion over a wide range of voltages. Vt is the thermal voltage, which is kT over Q. Okay? Here the Vt. Vt is kT over Q. We call that the thermal voltage. And the base current is also related with the same fashions, but the base current is going to be proportional to this 2 in the exponent at low levels. So beta going to be decreased at the low levels, and the high level effect will be discussed. That happens at the low level. And the high levels of base and collector is going to be discussed in the next time. You know, the next section is for that. So we call that the roll off of the beta as we decrease the beta values is going to be decreased, at the low levels of emitter base voltages, and we call that roll-off. So next section is going to be high level effect on the beta, and then that is going to be discussed on the Wednesday. You guys have this contents in your textbook? You do? You have that? Okay, this one is we in this class we just cover the basic operation. We have just covered the basic operation. Basic operation. And then today we have discussed about this one we have done last time, and then today we have talked about the current gain. And then on Wednesday, the next lecture, we're going to talk about the high level effect. High level VBE effect. Okay? And then in this current gain, we have the collected current, which is proportional to the e to the VBE over VT, usually, but it has three factors contributing this collected current, and one is the recombination in the base, and then a hole injection into the emitter, and the last part is recombination in the space charge regions. Okay, and these two can be presented as something like this, but the recombination in the space charge region, the current now is going to be proportional to the BE over 2 VT this time. All right? So if you plot the current with respect to the VBE, then that wide range of emitter voltage, it's going to be something like this, that is VBE over VT proportional, that is a slope corresponding to this. But here, if you plot, this is a VBE over 2 VT, okay? So at this low level, now this one is dominating this one. So at low levels of base and emitter case, this one 2 VT is going to controlling the gain, current gain. Well, the low levels space charge region recombination is important, and then that means that the hearing aid or pacemakers, which has to be operated in small signals, those devices, the space charge region recombination has to be more important than anything else. Okay, if you want to have a good hearing aids or pacemaker, things like that, then you have to do something to make the emitter-based space charge recombination as small as possible by controlling the fabrication parameters. Okay, on Wednesday, let's begin to discuss about the high-level effects on the beta, okay? And that are going to Early effect and Kirk effect, things like this. All right, and then we're going to wrap up the bipolar transistor operation chapter. And then from the next week, we're going to talk about the ULSI of bipolar. Okay? We are going to move to the miniaturization of bipolar transistors and the electrical characteristic change upon the miniaturization are going to be the topic of the next week lectures. Okay, have any questions? Okay, do we have a problem to have a class on the Wednesday? This Wednesday is not a holiday, is it? No. Okay. So I'll see you guys on Wednesday then.